Okay, so mathematical biology. Okay. So you are working on some neuroscience related thing or like with something other, computational neuroscience. Okay, it's not decided. Okay, yeah, I think I should read first. Share my screen. Okay, so this is the last module, and like, we have reached the end of the course. I hope you all have all like watched uh, the lectures, and hopefully you might have learned a lot about MATLAB. MATLAB is just a programming language. You might have learned a lot about numerical methods and how numerical methods can be used to solve problems uh, instead of using the analytical methods, like how these can be efficient in many ways, and how these can also prove to be detrimental if they are not used properly. You don't use a particular method instead of a particular method for some kind of a problem, then you might get some spurious results. So that's kind of a thing which you might have seen like when professor was explaining the class or while you were doing uh, your own coding for the assignments or like for the practice. So, so there was a lot to learn in this course, like major things which you might require in your like because I know both of you are PhD scholars. So most of the things which you might require while solving your problems, you will need these numerical techniques. So it's like if you are not doing something analytically, but like if you are solving any problem numerically, then you might need this. Like, of course, like there are like higher like higher order concepts or problems which you will solve and which you might require like you might have to use like something like computational fluid dynamics or FEM or some other things, but those all things are like based on these things which we have learned in this course. So if you have learned these things properly, like if you have learned central difference for solving PDEs, or like if you have learned the Ranjay-Kutta method, all these things, so you will find it uh, easier to learn other things too, like finite element or the other computational fluid dynamics, or finite difference or finite volume difference. So you can build upon these concepts and you can learn a lot. So, so it's like the objective of our course was to like introduce MATLAB for solving computational problems, and then using those you can solve any engineering problem or like any research problem. So MATLAB is like a proprietary software. So like we have to get the subscription, uh, like we have to pay for it. And like, of course, we get a lot of services because of the subscription we take. Like they have a good ecosystem, like a lot of developers work on it and they try to develop every day, and like they try to revise the versions. Like I think in a year, like you get two versions of MATLAB with better performance and all. So like uh, that's a good thing about using the proprietary software. So and also like if you are like if you don't have the subscription of MATLAB, like the same things like the same thing which you are coding in MATLAB, you can also code in Python or like the other programming language. The algorithm remains same, but just the language changes. Like everything is like same. Like if you are writing a for loop here, like there also you'll write a for loop. If you are writing a function there also you'll write a function. But like uh, there will be a difference in syntax of how you write a function in MATLAB. And Python. So like that's not a difficult task to go from MATLAB to Python. Like, you will find easy. Like if you have learned if you have learned one programming language, uh, like and you know how to write an algorithm and how to go step by step to solve a problem, like how you can break down a problem into various steps. If you know these things, you can easily like learn the basics of a programming language in 3 4 days, and you can code. Like it's not a problem at all. So that's why this course will be like a lot helpful to everyone. So who wants to solve computational intensive problems uh, in engineering or like research. So like I think first 2 3 weeks we just learned about the basic structure of MATLAB code, arrays, and MATLAB functions and scripts, and then we wrote also uh, codes and like learned a little bit of debugging. Then we went to machine precision, like least count of MATLAB, like, and then we also had like uh, iterative approaches, all these things like direct approach, multi-step, all these iterative approaches to solve linear equations or nonlinear equations. And then we also saw how errors occur and how they propagate when we do iterations. All these things we learned, and like then we went to solving linear and nonlinear equations, and then we went and learned differentiation and integration. Then we also learned about curve fitting, like we learned regression and also interpolation. And then we learned about differential equations. How do we solve a ordinary differential equation? How do we solve a ordinary differential equation initial value problem? And how do we solve a boundary value problem? All these things we learned, and like uh, so like we have seen like while we were solving these problems, we were using multiple approaches like uh, while we while we were doing like solving partial differential equations, like we were also using uh, OD15, like we were combining central difference with OD15s, or like OD15s means OD like or OD45, which means like you are combining RK4 with our what is this central difference. So different things like when we solve our research problems or like engineering problems, we have to use like in the same problem we might use uh, linear equations. We have to solve them, and like there only you might have to use some kind of numerical integration or differentiation, and there itself like you might use curve fitting. So these kind of things, like whatever we have learned like individually, like we have learned these things in a segregated manner, but like they can be used in a combined way also. So that's what we did. So like like so one thing I wanted to tell is like we also have a session tomorrow from 6 p.m. to 8 p.m. And like uh, there we will try to cover a few things which I have not covered. Like I couldn't cover, I think, the tridiagonal matrix uh, algorithm. So TDMS algorithm, I couldn't cover it clearly, and also I think differential algebraic equations haven't covered. And we also will try to like the main goal of that session is to summarize everything. Like like today also we are doing that, but like today, like tomorrow also we have a session like uh, revision session kind of a thing. Like if you want anything uh, for me to explain to you, like which you haven't like got a clear picture in this course, uh, please let me know here, like in the chat, or like you can tell me. Like I will note it and I'll make sure uh, I'll explain to you tomorrow. Like any specific thing which you want to revise or like which you haven't understood, uh, or like if you are looking for something new which hasn't been taught in this course and you might want to learn, like, and if you have any doubts regarding it, all these things, you can let me know today so that I can prepare better and explain to you. Otherwise, you can come like if you are like not getting uh, any doubts today. You can obviously you can join tomorrow and like you can ask me. I'll try to explain whatever uh, you ask. We'll try to see how we can learn about those things. I hope you'll join the session uh, tomorrow from 6 to 8 p.m. And then we have also like these are like few examples, just a few examples. So we have seen while we were solving this uh, OD boundary value problem, we converted a boundary value problem into a initial value problem uh, in the shooting method. Like in the shooting method, we try to uh, like in the shooting method, like you have two uh, boundary values like this, and we have to so we have to convert this into a initial value problem. So what we'll do is like we won't take this boundary value and we will convert, like in addition to this, this is one initial condition, and we can also write another initial condition, that is dt by dz at z is equals to 0. Like we will assume something and we will solve it. Like we will solve it and we'll try to guess this. We'll try to get this value from the solution. At t is equals to z is equals to at z is equals to 1, what will be the value of t? We will try to guess. And based like we will take two values. Like we can use the Newton-Raphson technique, or like we can also use the bisection method. Uh, and this becomes a nonlinear problem, and we can solve it. Like so, we have to minimize the error, which is the predicted uh, t predicted at z is equals to 1, and t exact. This is the t exact value. T exact at z is equals to 1. So this error we have to minimize. So that's what we do in the shooting method. We just try to assume this uh, initial condition. So as we know, like we convert this into two. We convert this into two. Like we can take this. Like we can write y is equals to dt by dz, and we can make it into a uh, assignment number 12 question number 12. Assignment number 12, question number 3. Okay. Okay, we'll look into it. We'll just uh, we'll just see what we have, what was covered in the lecture, and then I'll go through the problem which you have. Okay. So we convert this. ordinary differential equations, ordinary differential equation of second order into ordinary differential equation of uh, first order. So like you can take y is equals to dt by dz, and we can write like this t and y. So like we can x dot is equals to, sorry, is equals to y, and this is equals to gamma into p minus. So like these two become our uh, two ordinary differential equations, and we can use these two initial conditions, which is t of z is equals to 0 for this, and t dt by dz of z is equals to 0. We have to assume this, and we can solve this simultaneously uh, to get our solution for the ordinary differential equation initial value problem. And then you will predict the value of t at z is equals to 1. And if you get within the error like tolerance, then it's fine. Otherwise, you have to revise it. So that's what we do in uh, shooting. And then we have seen method of lines. So this we have seen already in the uh, last week. Like we solved uh, this uh, method of lines, like the same problems we have solved. So I won't go into this. And like same thing, like we convert this into a central difference. We convert this uh, second order derivative in space uh, to using the central difference formula, and we get some n number of differential equations, ordinary differential equations, initial value problem, and then we solve it. So, and then we saw we solved the Newton raphel. We saw how we can use numerical differentiation. Like if you don't know this f dash of x, like here you can simply get it like 1 plus 1 by x. But if you don't know this, like you can use the numerical differentiation uh, to solve to get the derivative and then solve using the Newton-Raphson method. Like we'll see the code, like how we wrote it, and then we go into like this is a uh, like here we saw how we can use uh, like this is an this red dots are the experimental data. So when what happens is like when we do experiments and we collect some data, so there is like noise which is present in the uh, experimental values, like just like because of environmental factors, like or some kind of uh, like precision issues in the sensor. Like there might be a number of reasons, but like uh, there will be a little bit of noise. Like we as much as possible we try to avoid it, but but we can't. Like there is the inherent noise present in the experimental observations. So like these are the experimental values, but this is the actual actual values. These are the actual values. This line of blue line is the actual values which should be the solution, and these experimental values should fall on this line. But obviously this has been done theoretically, and these values have been obtained experimentally, so there is like some kind of error between them. So like this error is not that much here like in the predictions, but if we do differentiation, like if I want to get the differentiation of my curve, if I want to differentiation of my process at various points using the predicted values, and like if I'm getting the differentiation using this experimental values, numerical differentiation, there will be a lot of difference. Like due to this noise which is occurring in the experiment, uh, it will uh, it will like deviate my uh, like differentiation values, numerical differentiation values, like very hugely. So somehow I have to remove this noise, or I have to like reduce this noise from my experimental data. So for that we use like lot of different techniques, like you can say filtering, or like you might have like if you have, you might have heard about Kalman filter or something else. Here we can just use like linear regression, or like regression, to just minimize the error and fit a line which passes through this fit a curve which passes through this like experimental values. And from that, like that will be a like when we do regression, like we try to minimize the noise. Like if you know regression, like you will know that like this is just like we try to minimize the sum of least squares. So that's what that is one way of reducing the noise. So like we try to do regression, and then we try to find out the differentiation of the experimental results, and then you can see that there will be much less difference between the differentiation of the theoretical data and also the experimental data. So numerical differentiation of noisy data has large errors, and so we do the curve fitting using regression. So that's what we do. And then we have seen uh, PDs in multiple variables. Okay. So in last week, we just had one variable. So like like only this kind of equation was there, like only CA was there. So here we have like multiple variables. We have CA, CB, and CC, and we have three transient differentiation partial differential equations. So we can solve it using method of lines. So here like there are conditions which are given, like C uh, at the boundaries, C like CA is uh, and CB is equals to 1, and then we have also this initial condition which is for all CA for I for CI for CA, CB, and CC at time t is equals to 0, everything is 0. And like what we can do here is like we can just convert this, like let's say at some point I do C by do T at I Z, yeah, you can say, yeah, at Z is equals to Z I. So we can write it as CA I plus 1, CA I minus 1. It means like I minus 1 when I say it, like at Z I minus 1, then can have like this is H, this is CAI and CEI. So like I have a domain like this, like I have divide like whatever Z I have, Z is my domain. I will divide it into n parts, like 1, 2, 3. So I'll have Z1, Z2, Z3, Z4, like that, like up to Zn plus 1. Like if I divide it into n segments, I'll have n plus 1 nodes. So I'll write this for each Z. Like I'll start it from here. Like I'll write it for each Zi, and we like we'll write it till the end. So we'll do it, and then we will have how many, like uh, Z Z22 and Z22 Zn plus 1. So we'll have n ordinary differential equations, initial value problems. And if we solve them using like OD45 or OD15 is, then we can get the solution of this. Uh, we can get the solution of this partial. So that's what we were doing uh, last uh, last week. Like here, like in this problem here, we in addition to CA, we also have CB. That's the difference which we are getting. So like this becomes third, like same for CB, you will write the same thing into CB plus 1, I plus 1, and CB I minus 2 by into CA I and CBI. So you will get here. So for this, you will get some like uh, like for CA, you will have some how many values? N plus 1 values. For CA, you will get n plus 1 values. For CB, you will get another n plus 1 values. And for CC, you will get another n plus 1 values. So like we take all these equations, differential equations, like this goes on from Z2 equations here, n equations here, and for DC also you will have n equations. So basically, you are going to solve three n equations at the same time, and then you will get the solution. So that's what we were doing. Uh, like last week also we were doing the same thing, but in addition to CA, we have CA and CB and CC also here. So and the solution vector like here we have assumed like this. So this is for node 2, like in the solution vector, we will, when we solve these equations, you for node 2, node 3, for node 2, what is the CA value, what is the CB value, and what is the CC value. For node 3, what is the CA, what is the CB, and what is the CC value. So up to n plus 1 you'll get. So basically, you will have how many n? Uh, 3n values in this vector. So earlier we were having only n. Like here we are solving three uh, partial differential equations. So which are like these three partial equations are on same domain z. So we will get 3n equations. So that's what we have learned uh, this week. So let's see the codes which we have written. Okay, I'll share the screen. Any doubts in this? Any doubts in this explanation which okay, seems you have understood the methods? Okay, okay. So I hope you can see the screen, right? Okay, fine. This is the assignment. Okay. Before that, we will see what we saw here. So this was the first thing we were solving nonlinear equation using the Newton-Raphson method. So we know that in Newton-Raphson method, we have xn plus 1 is equals to xn minus f of xn divided by f dash of xn. So like, if you don't know this differentiation of this, then we can use numerical differentiation. So like instead of taking df is equals to 1 by 1 plus 1 by 1 x, so here we are taking the numerical differentiation of this function, so which is nr func. So we have nr fun, we have nr fun x plus h minus nr fun x minus h by 2h. So we are using the central difference formula for getting the first order differentiation of our function, and then we will divide it with this with the function value which is f. So like just we are replacing the analytical value, analytical differentiation with our numerical calculation of the differentiation. Here additionally we have to give the step size. Like here we are taking a step size which is very low, which is 10 to the power of minus 6. So obviously when you solve Newton-Raphson, you have to give initial value which is 1.2, and this is the tolerance. So like if the error goes beyond below this, we will stop uh, iterating. So like in Newton-Raphson, like if we are doing like lot iterations, like going after like uh, from one iteration to the other iteration, like if your x value is coming like very near, like if you are getting 1.2 in one iteration, then if you are getting 1.2 again, like it means like your solution is converging. So that's what the error is. Like you can see x minus x new. So x is nothing but the old x value. So x new is like after calculating what we get. So here, if we run this, we can see uh, we are getting like x is equals to 7.09 39, and this error is like large. Like we are getting a huge error. Like now, in the second iteration, we are getting a little bit less error, which is 3.6491. And then if we are doing the second iteration using this value as x, so the new value which we get is 3.1518, and this error is reduced. And like you can see, these values are like getting closer and closer, and our error is getting reduced. So now our like error is less than the tolerance which we have taken. So this we can take as the solution of our problem, which is 2 minus x plus log x. So that's how we solve using Newton-Raphson. So this you can also do for multiple uh, multiple variables also. Like in multiple, this is a two-dimensional function. You can do it for various other problems also. Like the principle remains the same, but if, if we have like if you have two variables x and y, then it becomes like instead of differentiation, you will do the gradient of the function. So nabla f, you know. So so that's what we can do. Like here we have solved it right. So we can now just I will clear like this. Okay, I can clear this value, but I won't clear the workspace. So instead of this, if I take, let's say, if I take df is equals to 1 plus 1 by x, uh, now if run it, oh, it's getting something else. Oh, I think this is minus differentiation is minus 1 plus, yeah. So forget this. So this value and this value. Like you can see, we are getting the same solution. Even like if you are using the analytical differentiation formula, which we got, which we do by hand calculation, or like if we use the numerical differentiation technique, also we'll get the same thing. But like you have to make sure that this h value is like sufficiently small. Like if you can't take this, like say if you take h is equal to 0.1, like, yeah, we are getting good good agreement here too. But like if I take x is equals to 1, so we are getting some kind of imaginary value. But yeah, so we are getting it. So if, like now it is taking like two more iterations more. Like so h value if you take small, then it will be better, but it should not go beyond the machine precision and like sometimes taking too small is also not good. So sufficiently small you have to take. And then we have seen this uh, problem of experimental values and the uh, R measure is the measured values and R ideal is the theoretical values, like which are without noise. Like R measured has like noise which might happen, like which might occur due to some kind of uh, like errors due to environmental factors or something else. So if we are like doing the differentiation, like we are doing the differential equations of the ideal and the measured values, like up to this, if I run this code, uh, like I'll just write EMC clear all and close. We'll run up to only here. So here you can see the first value is the uh, differentiation of the measured values, and this is the differentiation of the ideal or the theoretical values. So initially, like you can say, okay, this is not that much. These two values don't have that much error, like for the initial time, and then like as time goes on increasing, like you can see the error is like getting more and more. Like uh, so, that's what uh, will create problems in our thing. So we have to be like this. This is our thing, and we'll just mute this and just comment this. And then yeah, so you can see the difference here, like numerical differentiation on the second value is like very huge. Third value it's fine, but like here again it is like very huge. So this is not very good. Like if you are taking your measured values and you are like calculating the differentiation, like sometimes you might need like based on the measured values, you have to plot something, and you have to also get the slope of that curve like at different points. Uh, and you might want to use in some other uh, in some other in some other point in your code, like in some other point in your solving problem, in some other step, like so this is not very good. Like you cannot take noise and calculate the differentiation. So somehow we have to get rid of noise. Like obviously we cannot get rid of it completely. We can try to suppress it to a certain extent. So that's what we will do here. Like we will do regression. So we will do regression and we'll try to fit we'll do regression and we'll try to uh, fit a curve, which best fits these measured values. So we'll see how we do it. Like we have already seen how to do it. So we'll take y as a y vector as these values of our our measured or the experimental values, and x is something which we will take like we have already seen like in regression we take this kind of feature vector, this we call as a feature vector, a feature matrix, which will have ones on the first column, and then we will take t, and then we will take t square. So we are basically here trying to fit a second order polynomial or second order curve or like parabola, whatever you can call it. So if we do, we know that we know that x into our phi is the y values. So we don't know what is phi. Phi is nothing but our coefficients of the polynomial, which is a1, a2, or here you might you can call it as a naught, a1, and a2. So that's what phi is. Like we try to calculate these values. So for the polynomial, we try to like we are trying to fit a second order polynomial. We have to find its coefficients. So after finding its coefficients, we can get the differentiation. So this is the differentiation of the regression. Uh, like after fitting the curve, like we are getting the differentiation of that curve. So this is the differentiation of that curve. So a naught plus a1x plus a2x square, right? So a naught, if you differentiate a naught with respect to z, then it's 0. And if you differentiate like a1x with respect to x, we'll get a1. And like if you differentiate a2 into some x square, or like here t square, like you'll get 2 into a2 into t. So that's what the differentiation is. So, and we'll also get this numerical differentiation of our ideal or set theoretical values. And like if we run it, we'll get the values, and you can see uh, like I'll just make this and I'll run this. So these are the differentiation various differentiation values which we are getting. So like there is not much like uh, error in like all the things. So the error we can reduce in our what is this numerical differentiation of measured values. So compared to the earlier uh, part, like here, like uh, if I just suppress it, and like if I just run it, oh, it's getting clear, right? Yes. Or I'll do, yeah. So these were our initial differentiation uh, comparison while directly using the measured values, and these were the numerical differentiation after fitting the curve. Like you can see that these two values, like here this was 0.36, now it is like 0.28. Earlier it was like 0.26, like now it's like okay fine, difference is not that much, error is not that much between these two. Like here also it's like the error is like much reduced. So here we are using regression and also numerical differentiation. So like basically we are combining two different things which we have learned. So that's what we are doing, and then uh, we'll go to our next part. which was solving this multivariable uh, partial differential equation using the method of lines. So here you can see uh, we have defined all the values which were given, like length of the reactor is 1 meter or like 1 unit, and we are dividing it into 50 segments. So that's why H we will get L by N, and initial values, like because we will solve this uh, using the OD15s, like odd initial value problem, we should have initial values, like all the initial values uh, are 1. So like it's given in the problem, like we saw Ci 0 is equal to 0. So we are taking all the initial values as 0. And we have to first define the function which gives us the uh, which gives us the ordinary differential equation. So like this is the function which we are writing. This will give me 3n plus 1. Yeah, 3n 3 into, yeah, 3n, yeah, 3n partial differential, 3n ordinary differential equations will get. So all these values are there, like at the inlets values of our uh, this boundary values of C are like 1.2, 1 and 0. So these values are given, and then we have to divide it into n segments. So length of y is like y will have uh, how much like uh, y will be having 3n, right? So 3n is the size of y. So we have to reduce, like we have to get the number of segments. So if we divide it by 3, you will get the number of segments, which is n. And again, you have to get the step size, which is L by n. And we will have CA. So initially, we'll take only the values which we are getting, like which we are like calculating in this solution vector. So in the solution vector, we won't have the boundary values, like at C in will not be there. So because we are solving only from like like let's say if you have Z is equal Z1, Z2, Z3, Z4, Z5, Z6 up to Zn. So we are solving only for, like we know Z1 already, so we are solving from Z2 to Zn. So that's why this Y won't have initial values. So then we will concatenate this list of CA with the Cn values, and then we'll have we will get the differentiation of CA with respect to T. Like we will define these vectors, like each will have n plus 1 uh, differential equations, right? Like for CA, we'll have the n plus 1 differential equations. We have it because we have divided into n segments, we'll have n plus 1 nodes. So that's fine. So, but we will only take it we want we do numerical differentiation only from we apply central difference only from z is equals to 2 to z is equals to n plus 1. So that's what we do. So we are using the backward difference formula here. So we'll get all these values, like we are just using the backward difference for all the like partial differential equations. We'll get the ordinary differential equation. And then we will uh, try to do this for uh, n plus 1 values. Like this is for only for we will try to form a vector dy which has which includes all these values. Just give me a minute. So, so we'll try. What we will try to do is like we will just we'll just take this dy as an empty list, and we will try to add add differential equations like these differential equations one by one. Like we will add d by dc, sorry, dca by dt at point 2 and dcb by dci at point 2 and dcc by uh, what is this? dt at point 2. Like this, we will do it from uh, I is equals to 2 to I is equals to n plus 1. So we will get, so basically we will get 3 into uh, n. So we'll get 3. Somebody has put a message. Okay. So we will get uh, like 3n differential equations, and we have to solve all these 3n differential equations, ordinary differential equations, as an initial value problem. So that's what we are doing it here. We are using OD15s. So we are using OD15s. Like we can also use OD45s, and maybe might be because the problem is stiff here. Like I don't know how this is a chemistry problem. So like maybe this is a stiff problem. So that's why we are using OD15s. So we are solving, we are calling all these ordinary differential equations using this function. You will have 3n ordinary differential equations, and you have to give 3n initial conditions. So that's what we are doing here. And we also have to give the time span, and this OD sort uh, 15 years will solve and give us this, uh, will solve and give us the solution. So you will get the solution values from node 2 to node n plus 1. So now we can plot these values. So we can like take CA. So we CA, like we have to include the initial value, as we know like initial value is not included in the solution vector. Initial value or the boundary value at z is equals to 0, or at z1 this is 1.2, and this is the solution for like this is the like uh, uh, I think like we have taken this as like we have taken this for 5 time instance, right? Like this is for the first time uh, we are including this. So like uh, you can like we can just basically plot uh, one by one, uh, like 1.2 comma something you'll get, and then uh, at first time you will get all the values, like at time t is equal to 0 you will get all the values of concentrations of concentration of Ca at various points on the segment. So that's what it does. So like we can plot it for 5 time instance, like that we can do. So like this basically has Ca has 0 to like it has like values for various segments on the reactor. So like if that's like uh, that's how we can solve and plot. Like we'll just plot and see how we are getting the result. Like I think I should have included CLC, CLC, clear all, clear all, close all. No problem. Screen is visible. Yeah. So this is the plot which I am getting for concentration at concentration Ca. So the plot looks like this. So this each curve is for like for each point. Like this is for like one is for c is equals to 0 at time t is equals to 0. I don't know which one is for which one. Like you can check it. Maybe it should if I have included the legend, like it might have given. So then one curve is for 0 time at like uh, at time 0.5 at various points on the reactor, like because our reactor length is 1 meter, like we are going from 0 to 1 meter. So at time t is equals to 0, this might be the concentration levels, and at time t is equals to 1, this might be your concentration levels, and at time t is equals to 5, this might be your concentration levels, ca concentration levels. Then you can also plot this, the second plot here, like you can see this CB is also having like a similar thing, like basically all the concentrations are decreasing, like at various points. Like initially it might be like this, and like after after as the time passes, the concentrations might be decreasing. That's what it is happening. Like from one end to end, at the other end also they are like decreasing. Then we can also plot CC. Then it will look like this. So CC is this plot. So you can see CC uh, values are like increasing here, and then like they are increasing and also decreasing for some certain time instance. So how this is how concentrations are varying with respect to the length of the reactor. So this is with respect to the length of the reactor. So we are plotting it with respect to the length of the reactor. So that's how we can get the idea of how our solution is looking like. So that's how we can solve partial differential equations of multiple variables. So here multiple variables are CA, CB, and CC. So now we can uh, go for the problems in our uh, I think you wanted like uh, this, right? Uh, assignment. So uh, we'll take a 5 minutes break. I just want to uh, drink some water. I'll come back, and then we will see this practice assignment and also assignment uh, 12. If you have any doubts, we will see. We can see how we can solve this. If you have any doubts also, you can ask me. Just I'll come back in 5 minutes. Okay. You can also take a break. I just want to have some water. I'm very thirsty. Okay. Uh, so Abhishek was asking this. Abhishek, are you here? Can you hear? Yes. Okay. So this has two partial differential equations. I mean, like, and also partial differential equation in two variables, and we have to solve it. So, so we'll just take our code which we have written here, okay, and we'll just copy it, and I'll just make the changes here itself. Okay, save example one. So length is same. The number of intervals is 50. Okay, everything is same. U is 0.1, 0.1 here, and K is 0.5. Okay. And these are our initial values. We have only two boundary values, which are at z is equals to 0. Okay. Hmm. There is some kind of is this should also be Ti. I don't. We'll just check it. These are CA is 1 and CB is 2. And we have only two, so we'll just remove CC. There is some error, I think, in this. Non-graded, uh, yeah, everything like this. This should be T. Uh, yeah, otherwise we cannot solve this. This should be T. Mm, mm, yeah. Okay, this is one, this is two, and what is there apart from this? This should not be there, and R is K into CACD square. Yeah, we have to just square this, and this we will remove. and this is already there. Like this is the same thing. Here we are having minus r. Okay, minus r is fine, and this is minus 2r. Okay, yeah, everything is there, and this is 2 into n. This is fine. Yeah, this is not there. This is not there. Backward difference. Yeah, we are using the backward difference. Time t is equals to 5. We have to use, okay, 15, yes. Okay. So we are doing it, and we will just save this and solve. There is some error. What is the problem? Index must not save before. Ah, this we have to, now we have to jump in steps of 2 here. Fine. Okay, now what is the problem? Okay, this is not there. Okay, sorry. Vectors must be, okay, what is it? L by M. Okay, this should be steps of 2, and these are like, what are the values? 1 and 2. So this is how we are getting these plots. Like these are for like, obviously for different, this is for CA and this is for CB. This is for CA and this is for CB, the dotted lines one. So in this we have to, like, you will get the solution vector. So in the solution vector, we have to find at z is equals to 2, what is the value at z is equals to 0.2, at z is equals to 0.4. Like this we have to tell. So either you can just, we can, what we can do is like, we can just, uh, uh, at, say, if uh, sorry, if x, sorry, I time Time is equals to 5. This should not be there. Display. Display. We have to basically display the last 0.2 means how do I write on the right and use something like this. Yeah. Okay. So 0.2 is the, I think like what our step size is 0.002. So if you take, I think uh, h is equals to L by N, right? Let's say if I take 0 to 0.002 to 1, I take I take this, get this thing. So 0.2 is, I think, how much? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Uh, so we are starting from here. 1, yeah, okay. Okay. Mm. 1, 2, 3, 4, 5, 6, 10. So I can display y solve, solve approach I time, and in this I can display the 10th value and 1, 2, 3. This also has like, you have to go like seriously, like uh, this will become 20. How many? I can just write that. Hobbies. at z is equal to 0.3. And what was so these are all for t is equal to 5, so I am not using it implicitly, right? And then we also want the value of 0.4, right? 0.4. So this basically will become 40. This will become 40. And z is equals to 0, and I'll write another c. c and this is also c. So first I'll write print all the CA values. I want 0.6. So this is 0.6, and this is another 60. So in this solution vector, the uh, 20th element will have what will be the value of CA at 0.2. So like that we have to do. So then I also want to print my CD. So, CD. So it's like you have let's say, like 21, 41, and 60. Basically, we have something like this, right? So, that only. So let's like uh, what z is equals to 0.2, we'll have uh, let's say we'll start from z is equals to 0.2. This is our first solution which we right. So for that you will have CA. Yes. So this will be, let's say you can take like first value in the solution vector and it is the second. So then you will have z is equal to 0.00. So then you will have CACB, which is like 3 and 4. So like this, if you keep on doing it, like uh, you will get one, one to how much like should be the logic here. 5, 1, 3, 1, 3, 5, 7. These are all the C values I'm writing for various segments. 17, 1, 2, 3, 4, 5, 6. I have to write here 19. This is 19 and this is 39 and this is how much? Uh, 14, 15, 15. And these are 20, 40 and 6. So now I can like just uh, make this also 10 run. So you can see these are the values which are which I am getting there. 0.35, 0.24, all this. So these are the C values. These are the C. You can also check CA and CB, but this CA is only for the last time interval which we have seen. So we can also do one more thing. Like, like here, what this is doing is like this CA after each time, the CA is like getting reset. So instead of that, we can like take let's say some other like here some kind of like empty vector. Like CA is just some empty list. I'll take. And what I can do is like I can store this all these things like, so that it might be clear. I'll also do the same thing with C, so that I won't end up losing the values for previous time. What we have calculated for previous time also gets saved. This will create a big problem because again I have to change again some code. So what I'll do is I'll keep this like this. So CA for all time. CA for let's say for all times. CA TL. This I'll make C for all times. Not for just for each time, but for all time. So now I can take this. CAT will have we have the previous task. Similarly, we can do it also for CBT. This gem size. We just run it and see the so this is creating more. What thing I can do is I can take in this separate column. Yeah, now you can see this is for each time. Like this is for t is equals to 0, or these are all my CA values. And this is for time t is equals to 0, these are all my t. And this is for time t is equals to 3, these are all my C. So like this is for 0.002, 0.004, 0.005. So the 10th column, this is my concentration at 0. How much was it? Okay, we are including this also, right? The first thing, okay, okay. There is another change we have to do. Okay. So what I'll do is I'll just take this part. I don't want my boundary value to be plotted. Uh, value is I'm not including boundary value. See. So this is our concentration at the 0.00 0.2. So 0.2 is like z is equal to 0.2 is at the 10th node. So not the 10th but the 11th node. So like if you take divisions, like if you go in steps of 0.2, like z is equal to 0 is node 1, like if you are jumping in steps of 0.002, you will get at the 11th node, like because I am not including z is equals to 0 here. So like that's why like this 10th cell in this is nothing but like at the 11th node. So and at time t is equals to 5, this is my concentration. So like similarly, I can also do for this thing, which is my 20th. So at 20th, like uh, 20th cell, which is the 21st, what do you say, 21st node, this is my concentration. CA is 0.2499. Here's like, it has like adjusted a bit. So, and at 0.6, which will occur at 60, so there is no like, it will occur at, yeah, 30. Sorry, so it will occur at 30. So this is my concentration in CA. So like that, if you are like jumping 0.8, you will get at 40. And sorry, 0.8 you will get at how much? 10, 20, 30, and 0.2. We have how much? 50 seconds. 50. Okay. At 10, we are getting 10, 20, seconds, right? I have how many seconds? Let's take some kind of 0.8 up to 1. Create a list. List. Yeah. At 11th, you are getting 0.2, and at 21, you are getting 0.4. 30, you are getting 0.3, and at 40, you get 41, you get 0.8. So we are not taking this into account. So I'm just saying, like, instead of 40, I'm taking 41. 41, I'm saying 40. Yeah. So, so you'll get 40, you get this. What 0.8, this will be my value. At 0.6, where is my 0.6? This will be my constant. So similarly, we can also check for CBT. So this is for uh, time 0, time 1, and this is for time 5. And this I'm doing it from z is equals to 0.002 to 0.00. Sorry, this is z is equals to 1. Like the 50th cell is 0. Z is equals to 1 meter. So like each column is for like solution for each node. So you can check accordingly, like which node will give you which point here. Like 0.2 is the 10th value. So from that, like, you can print it like this. Uh, is this clear? Can you hear me, Abhishek? Do you have any doubts in this? Video is not running. Abhishek, are you there? Can you hear me? Yes. Is this understood? Okay. Do you have any doubts here? Asif, do you have any doubts?
Hello, sir. Good evening, sir. No doubt,
Yeah.
sir.
Okay.
Sir, you were saying that tomorrow we are going to have doubt. Means once again, one more class.
Yeah.
What time are you planning to, sir? Because already Chandra madam said we will be having, means last Friday when we had class, she
Ah,
said tomorrow around 6 o'clock it will be there on Wednesday. What
yeah,
time
yeah.
you are planning, sir?
I have also given 6 to 8 p.m. only. So
Oh, 6. So can't be time bit different, sir, so that we can attend both the sessions. Is it not possible?
what time will be suitable?
Any time, sir. 6 to apart from 6 to 8.
Apart from 6
Because
p.m.
usually what I have a habit is I attend your class also and her class also is a maximum benefit. Others P also sir is also taking class, but that time since I have enrolled for other course, so I have to same time it is Monday 6 to 8, so I have to always go for that course because anyway I can go with yours and madam class.
Okay.
And sir,
Hmm.
yeah, one request, can it be bit because since tomorrow she's taking, can it happen like some other day so that we can go through all the concept and then clarify the doubt in case
Other
it's
day.
possible?
No, I think like the we have got the instruction like today tomorrow is the last day. Like we cannot go
Okay,
beyond
oh,
tomorrow.
fine. Then try to
So,
just know give some other timing,
uh,
please.
so like that's why like that is the last date. So I cannot go beyond that. Like they told like I think this Friday to this Wednesday they told they gave me time.
Okay.
So because I think you will be having exams also. Like
Yes, yes.
it's 20th after 20th also.
Exam will be
Uh,
from third and fourth.
okay, make sure. Okay. So they have told like, timing like they have already announced. So
Okay.
uh, we can do one thing like
Yes, sir.
7 to 9 is okay. 7 to 9.
Uh, can it be 7:30, sir? Because it's 6 to 8.
7:30 one. Okay.
Uh,
7:30 we can. Okay,
sorry,
7:30
sir.
we can. Yeah, yeah.
Okay. Yes, sir. Great, sir. Thank you, sir.
Okay. 7:30 we can. I'll like if the other guys like who are here, like if you also want to uh, start at 7:30, I'll try to tell them like that we are taking from 7:30. Like, if they announce it, it's good. Otherwise, uh, like because you can join at 7:30. Others might miss.
Okay, sir. Thank you.
Okay, so this the tricky part here is like only finding out the nodes and what is the position of that vector in your what is the position of that node in the solution vector. So that's what it is. Like we can also see this practice assignment, same problem is given. Similar kind of. So just so this is C power 0.7, A power 0.7 is for it is also 0. Uh, minus R. Uh, Same initial values are same. This is 1 and boundary values are is U 0.1 and A. So, and we also have we have to solve for same right. Mode I is equals to double. Same drop point. 0.8 also there. Yeah. A ED is only at 0.2. So I'll just see. This take 0.8 also. 0.8 is another 20 steps ahead. 20. Just run it, getting this plot for the solution for various time. CAD is this. So CA is 0.3869 is 0.5864 CV at 0.2 and 0.7 6 7 and 7. That's all. Next. Okay. Values are bit off. Why is this happening? Uh, Everything is fine. Just there is some kind of error. 0.1 is 1 and 0.5 and U is 0.1. There is some slight error. I don't know. Okay, okay, okay. I'll try to give the timestamp different. Uh, Give it like this, 0 to 5. We'll, we'll do one thing. We'll just remove these things. I don't want to plot here. Uh, Anything to be plotted and just display everything. This is end. For the last time, I have to get getting the same values. Just take the solution and just use. Yeah, There is a lot of errors in this. Assignments are also there a lot of errors, I think. Nothing else is wrong. Everything is okay. What the answer they gave is wrong here. Okay. Two, zero. Oh, okay, 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 okay. This was 1.2. Now it's done. Small error, everything was. Okay. Okay. Now we are getting everything correctly. Yeah. 0.420. Okay. 0.6201. 0.523. Yeah, it's 0.077. 0.078. Yeah, this is also fine. Fine. Okay. There was a small error. I instead of taking power 0.7, I 0. Sorry, 1.2, I took 0.7. So everything else is fine. Yeah. So that's how we can go about solving the partial differential equations with multiple variables. Uh, I hope this was fine. Nasir, you have any doubts?
Sir?
Do you have any doubts?
No, sir.
Okay.
Thank you, sir. Thank you for all the clarification what we had so far. Thank you very much.
Okay. I like uh I don't know like this tomorrow's class I don't know how to. uh, handle this. We'll start at 7. Like if it is possible, like you can join this class, or like if you are like engaged there, you can continue. Yeah. Uh, I think 7 will be a good time. Like beyond 7, I cannot go. Then it will be
Okay, at least seven,
little.
sir. Yes, sir.
Yeah, yeah. We'll start at 7. Okay.
Thank you, sir.
Okay. Thank you. We'll stop it today.